This is the fifth video in a multi-video tutorial series using the FluCoMa toolkit to build a two-dimensional sound browser in which we can explore and perform sound slices in a two-dimensional space. In the previous videos, what we've done is we've taken a buffer that has a lot of different sounds in it. We've sliced up that buffer, finding slice points and finding audio slices that we then analyze, finding the average spectral centroid and average loudness of each of these sound slices, and then using those two properties of each sound slice, plotting it in two-dimensional space. In this video, we're going to replace these analyses with a single analysis called an MFCC analysis that'll give us 13 dimensions or 13 values that will describe each sound slice. And then we'll reduce those 13 dimensions down to 2 dimensions using a dimensionality reduction algorithm called UMAP, that we can then use those 2 dimensions to plot it in two-dimensional space. So I'll start by re-executing the code that we have from the previous examples. This code I have right here is not exactly what we left off in a previous video, but I'll link to this code in the video description so you can start from right here if you would like to. If you're starting from one of the other videos, you'll recognize all of the operations that are happening here. You'll be able to adapt your code very easily to look like this. So I'll say that the folder of sounds that I want to use as my corpus will be the folder of sound files that comes with the FluCoMa toolkit as example sound files. And then I will load all of those sound files into one buffer. And then because that buffer is going to be stereo, as we saw in the previous video, I'm going to sum it to mono. So I'll have all of those sounds now in a mono buffer. I'm going to take that mono buffer and find some slice points using FluidBufOnsetSlice. And it tells me that in that buffer, it found 1,478 slice points, which means that each slice has an average duration of about 340 milliseconds. So that sounds like a good average slice length for me to use. Now that we're at the step where we would do some analysis, I'm going to change what I have in my analysis code block here. I'm not going to use FluidBufSpectralShape or FluidBufLoudness. So I'm actually just going to delete all of these process blocking operations here, and we'll put in some other types of analysis. So I'm going to use the FluidBufMFCC analysis. MFCC stands for Mel Frequency Cepstral Coefficients, which is a type of audio analysis often used for timbral description or comparing the timbre of different sounds. And if you want to learn more about MFCCs, you can look at the reference page we have here on learn.flucoma.org. And it describes what it does and why you might want to use it for different applications. We also have an interactive demonstration. This describes a little bit more in depth how the MFCC values are computed using a series of steps down here to actually step through the process of computing the MFCC values. Using some real-time audio, you can see the Mel frequency spectrogram that is computed from that audio, and then the resulting MFCC values or Mel frequency Cepstral coefficients that are computed from the Mel frequency spectrogram. You can also adjust the spectrogram to see what sort of MFCC values would result from different shaped spectrograms, and then also adjust the MFCC values to see what kind of spectrums might produce different MFCC features. To compute the MFCC features on this buffer, we're going to do it just like we did with FluidBufLoudness and FluidBufSpectralShape. We'll say that the buffer it should analyze is on the server S. The source is going to be our buffer called source that has the audio in it that we want to be analyzed. The start frame and num frames, again, will be the start position of the sound slice that we want to analyze, and then the number of frames in that sound slice. The features argument here is going to be a buffer that we're going to make to store the MFCC values in after each slice is analyzed for MFCCs. So I'll actually just delete all these buffers up here and we'll remake them. So var MFCCs is going to be a buffer that will put that analysis in. We'll specify the number of coefficients should be 13, which is the default, but we'll be explicit here because later you might want to try increasing this number, which will give you more coefficients that might describe the sound more specifically. And then also we're going to specify that the start coef should be 1. And we're specifying this here because coefficient 0, or the 0th coefficient, is a representation of the overall energy in a spectrum, and so it relates to how we perceive loudness. And in this case, we want our data set and our analysis to just represent the timbral characteristics of the sound slice, and we don't necessarily want to encode a representation of how loud the sound slice is, so that when we eventually have our two-dimensional plot, the sound slices are just organized according to their timbre relationships and not necessarily according to loudness. If we go back here and look at this Mel frequency spectrogram derived from this oboe multiphonic, and adjust this 0th coefficient, we can see that all it adjusts is the overall loudness of the spectrum. It's actually not changing the shape of the spectrum at all, just changing how much energy there is in these different magnitudes. If we were to adjust one of the higher order coefficients, we can see that it will change the shape of the spectrum, so really changing what sort of timbre is represented by this set of coefficients. By specifying start coef1, we're telling FluidBufMFCC that rather than starting at coefficient 0 and giving us 13, 0 through 12, we want it to hop over coefficient 0, start at coefficient 1, and give us the next 13, so 1 through 13. Now, once this analysis is complete, our features buffer, called MFCCs, will look like this. It will have as many channels as there are MFCCs as we asked it to return, and so since we said num coefs is 13, this will have 13 channels. It will have as many frames as there are FFT frames in the sound slice being analyzed, just like we did with buff spectral shape and buff loudness. And so now each one of these channels in the buffer is a time series of that coefficient and how it changes over the course of a sound slice, just as we can see these coefficients changing through time right here in the bottom right section. Now, because we specified FluidBufMFCC should have a start coef of 1, our buffer won't be shaped like this. Channel 0 won't be MFCC 0. Instead, channel 0 will be MFCC 1. And so we'll have 13 channels that contain the time series of our coefficients from MFCC 1 up through MFCC 13. Now, just like before when we had FluidBuff spectral shape giving us a time series of spectral centroids and FluidBuff loudness giving us a time series of loudness values, we'll have a problem if we want to use these analyses to compare these sound slices to each other, because some of the sound slices, being longer than others, will have more values, more analyses per sound slice. So just like we did before, we're going to use a statistical summary of these analyses to describe each one of these sound slices in the same way. And so we're going to find the average value for each one of these coefficients in our MFCC analysis. Just like we did before, we're going to use FluidBufStats. Our source buffer here will be our buffer MFCCs that has the MFCC analyses in it. We'll want to analyze the entire buffer because it contains the information for the current sound slice. So we'll leave start frame, num frame, start chan, num chans, all the default. And then we'll say that the stats buffer, where the statistical summary should be written into, will be called stats. I better make a buffer called stats. And then just like we did before, I'm going to use a select argument here to tell FluidBufStats that I want it to just return the mean values for me. Now remember that this buffer called stats is going to find 7 statistical analyses for each channel in my buffer that I give it, in this case the MFCC's buffer. So we'll have 13 channels, and it will have 7 frames for the 7 statistical analyses that it returns for each of those channels. So because in our MFCC's buffer, channel 0 is MFCC 1, we'll have the mean, standard deviation, skewness, kurtosis, low percentile, mid percentile, and high percentile of all the MFCC 1 values that are in that sound slice. In channel 1 here, because it is MFCC 2, we'll have the same statistical analyses for all of the MFCC 2 values that are in the sound slice, etc. Remember that the low percentile, mid percentile, and high percentile by default end up being the minimum, median, and maximum values from that channel in our MFCC buffer. Because we're using the select argument here to tell FluidBufStats to return only the mean value, the buffer that FluidBufStats return to us, the stats buffer, will actually be shaped like this, giving us as many channels as there are in the input, again 13, but instead of all 7 frames, just frame 0, which will contain the mean values. Now before we can add all of these mean MFCC values to our dataset, we first need to get these into a flat buffer, by which I mean not a buffer that has 1 frame and many channels, but instead a buffer that has 1 channel and many frames. So because I have 13 mean MFCC values here, what I want to have is 1 channel that contains all the mean values. Because I have 13 of them, it should have 13 frames. Luckily, there's an object in FluCoMa called FluidBufFlatten that will do this operation for us. So we will put in here FluidBufFlatten. And what I want the source to be is my stats buffer that contains that single frame of mean MFCC values. I'm going to leave start frame and num frame, start chan, num chan, all as the defaults because I want it to do this flatten operation with the entire buffer. And then my destination will be a buffer I'll make called flat. So now that I have these values in this flattened buffer, I can use that buffer to add a point to my dataset in the dataset called analyses. So now if I run this, we can see that it's analyzing these slices, again syncing every 100 slices. And here's our data set that has 1,477 sound slices and 13 columns, which is the mean value for MFCC coefficients 1 through 13, again skipping over MFCC 0. So now that we have this data set here, we could try to plot it with FluidPlotter. But FluidPlotter can only plot things that has 2 columns, because it won't know what to do with all 13 of these dimensions. So what we'll do is we'll use a dimensionality reduction called UMAP that will reduce the number of dimensions from 13 down to 2. We'll tell it the operation fit transform. We'll give it this data set called analyses that has 13 dimensions in it. And we'll give it another data set that once it does this dimensionality reduction and reduces the information to 2 dimensions, it'll write those 2 dimensions into this destination data set, which I will call UMAPed. So what FluidUMAP is going to do is it's going to analyze this data set called analyses that has 13 dimensions in it and look at those data points in 13-dimensional space. Now, of course, we as humans cannot imagine a 13-dimensional space, but this algorithm will compare all of these sound slices in that 13-dimensional space and find the relationship between those data points. What data points are near to each other, what data points are far away from each other, and create a tree data structure that organizes them so that the points that are near to each other are connected near on that tree, and the points that are far away from each other are connected farther away on that tree. Then it's going to take this tree structure and essentially toss it into 2-dimensional space, at first positioning all of these data points randomly in this 2-dimensional space. And when that happens, it might look something like this, at which point it starts iteratively adjusting the position of all of these points in this 2-dimensional space, trying to get the tree-like structure in this 2-dimensional space to match as close as possible to the way the tree data structure was originally organized in the 13-dimensional space. And once this iterative process of adjusting the position of these slices in 2-dimensional space reaches a certain level of quality, then it will stop. And we have something where we can see that the relationship between these sound slices will make sense in this lower dimensional space, even though they were originally analyzed in a higher dimensional space. Now, one thing to notice here is that the X and Y axis of this 2-dimensional space no longer represents any sort of musical representation. So it's not like one will be, one axis will be loudness and one will be centroid. But what we can hope and what we can sort of see here is that in this 2-dimensional space, the points that are near to each other because they were near to each other in the 13-dimensional space. And the points that are far from each other in this 2-dimensional space are far away because they were far away from each other in the 13-dimensional space. So now if we run this fit transform, and I'll put an action function in here. Oh, we have to make that data set called UMAPed and then run it. It'll take a little while to compute. The server bar will turn yellow here for a moment. And then it says done. And now if we looked at the UMAP data set, we can see that it now has just 2 dimensions. It has all the same identifiers as we had before, but now each of those identifiers, rather than being associated with 13 values, those 13 MFCC values, now it's associated with just 2 values. And again, these 2 values are not necessarily human readable in any way, but they will give us the 2-dimensional position where we can place all of these data points or sound slices to get a UMAP representation in 2-dimensional space. There's one more thing we'll do before we plot this, and that is we will still normalize this information, this UMAP information, before we plot it. And that's just because if we look here, we can see that some of these UMAP values go up into the 12 range and they go down to 3 here. So the actual range of these values are larger than our plot is by default set to display. We will take the UMAPed data set, and rather than normalizing analyses, we'll normalize UMAPed. And then our normed data set here will be the normalized values of our UMAPed result. And then we can fit a KD tree to those normed values, define a play slice function that we'll use to play back the audio slices, and then we'll plot it. Now we can see here we have an interesting shape, and if I click and drag around here, we can see that all of those sounds are clustered together. Here's a bunch of trombone sounds clustered together. Looks like that's all the oboe multiphonics. Some synth tones. Some more synth. Here are the bells. So we can see now that UMAP has organized them in such a way that we have sounds that have similar timbres are being sort of clustered together or grouped together in this two-dimensional space. The actual shape that we have here, these sort of like long lines of sounds, is sort of a common result of UMAP, in that it gives us these sort of tentacles that tend to move through the space in this way. UMAP has a couple parameters that we might adjust in order to change the result of our UMAP plot like this. And those are num neighbors, the default of which is 15, and the minimum distance, the default of which is 0.1. Number of neighbors refers to how many neighbors each data point should look towards when creating the initial tree data structure, essentially deciding how important or how many neighbors should be included in the local neighborhood that it is trying to create in the two dimensions. And the min distance argument is described in the original UMAP paper as a sort of aesthetic argument that you can use to adjust how the overall shape of the UMAP plot looks when you see it in two dimensions. So if we adjust this one, we can, if we put it up quite high, like 0.9, and rerun UMAP, and then renormalize those values, fit to KD tree, and then plot, we can see that this is a much more spread out space. So the min distance argument specifies the minimum distance that these points can be near to each other in the final resulting UMAP output space. And so by increasing min distance, we sort of spread out the data points more in this two-dimensional space, which might be very nice for us if we want to use it as a performance instrument, because then we might have a better coverage of our two-dimensional space that we want to browse around the sounds in. But what this also means is that we sort of lose that tight clustering of similar timbres that we were seeing in the previous plot. So that's a parameter you'll want to play around with and see what is going to be most musically expressive for you. This page is again on our learn.flucoma.org. It is our UMAP reference page, and it has a lot more information here about the different parameters, some resources you can dig in deeper to how the algorithm works if you want, and play around with these parameters in real time and see how it affects the learning process. So now that we've seen how to use dimensionality reduction to reduce a data set that has a lot of different analyses or features or dimensions inside of it to 2 dimensions so that we can plot it, there's a couple things we could try here. Rather than using MFCC analyses as 13 values, we could try increasing this up to 20 and see if that changes the way that our sound slices are organized in the 2-dimensional space. Rather than using MFCC analyses, maybe you want to try using all 7 descriptors of the FluidBuf spectral shape analysis and reduce those 7 down to 2. Or maybe you want to combine some different analyses, like take the spectral centroid, the loudness, and the pitch confidence, which come from the FluidBuf pitch analysis, and then take those 4 different analyses and reduce it to 2 dimensions and see how that organizes your sound slices in 2-dimensional space. So there's a lot you can change here in the analysis step to see how your sound slices will be eventually organized in your instrument. One important thing to note here is that if we have different analyses that have greatly different ranges, such as pitch, which could be up in the hundreds or thousands of hertz, and pitch confidence, which will always be between 0 and 1, it'll be important for us to use some scaler to make sure that those ranges are scaled into a similar range. Just like we were talking about in a previous video, if one dimension has a greatly different range than another dimension, the dimension that has the larger range will have a much larger influence over the distance between points as they're computed. And this will affect how UMAP creates the initial tree data structure and then ultimately how UMAP organizes these points in a lower dimensional space. It's also worth exploring if a scalar changes the way that UMAP organizes these MFCC dimensions. So you could use a scalar such as fluid normalize, fluid standardize, fluid robust scale on these MFCC analyses before passing them to UMAP. And of course, as we talked about before, there are different slicers in the FluCoMa toolkit that you can take a look at and see how the different slicers will find different sound slices inside of your source buffer. And of course, lastly, an important thing to consider is what is the corpus of sounds that you are analyzing and plotting. So you can always change what folder of sounds you want to hear, and of course, that'll give you a completely different performance instrument to play around with.